All right. Hello, everyone. Good afternoon, good morning, good evening, where you are in the world. It's 2023, and it's the first webinar of the year that we're organizing in our continuing series. So I'd like to welcome everyone. Before we start, just a few simple housekeeping rules that just tell you that this presentation will be recorded and it will be made available. So don't worry if you miss something. You'll be able to view it later and share it with other people. For what concerns the questions, there will be a full presentation. Just use the chat box to ask questions, and I will summarize them and I will interact with today's speaker to hopefully answer all your questions. Should there be unanswered questions, you're still free to shoot us more questions, and we'll try to get back to you and give you all the answers. So it's time to welcome and introduce Aurélien, our speaker today. Aurélien van de Kefkoop is a chemical engineer from the Institut Maurice in Brussels. He graduated quite a few years ago. He started with Hamers Technologies as a project engineer, moved on to project manager, is currently team leader, business development, and Aurélien has started with an array of projects, going from in situ projects in Denmark, if I'm not mistaken, some large mercury projects. It's been living quite a while also a big job in Singapore, and is now back in Brussels, where he's going to tell us all about a pretty exciting subject, often overlooked, which is how do we cool soil? We've talked a lot about thermal desorption. How do we heat it? It's all about the whole heating. And now, after when the heating is done and the soil is clean, what happens then? And it is an important subject. We get more and more questions about it, and there are different ways to do that. And so I'll just transfer the mic to Aurélien, who will tell you all about it. Aurélien, the floor is yours.
Thank you very much for this introduction. Thank you all for attending this meeting too. As Jan says, the first one of the year, and we wanted to choose a specific topic, which is basically a topic that no one talks when we are talking about thermal desorption. To give you a rough idea and a quick overview of what will be the agenda of today, I will just give a few words about the company, the technology, or principle, just to give you all the required knowledge to understand the different ways to cool it down. And we will then jump on the different methods of the cooling downs and a quick conclusion. Company overview. Our technologies today, in few words, 25 years of business. We are mainly a technology provider. We are inventing and patenting our own technologies, and we are based in Brussels. We are approximately 55 people. To give you a rough idea, almost 50% of the company is about research and development. We have our own laboratory. And of course, because we're inventing and patenting, we are also manufacturing the specific equipment dedicated to the technologies to remediate the soil. Here, quick overview. That's different clients and partners we have worked the last few years. Just to say a few of them, we work with Eni, with Ecom, with Total Energy, with KBC, with some also local partners. Here, that's a map where we, through our business model, which is we are only technology provider. So we make sure to give all the required knowledge to carry out remediation. We did many projects in the worldwide with the local partners, and there are some dots talking about the type of project we did. Thermal desorption. So what is thermal desorption? Because even if we have many technologies that we can propose you through Amherst Technologies, let's just focus on thermal desorption. And thermal desorption is a physical and chemical soil remediation techniques that works in different steps. But if you just want to remember something, it's we are separating the contaminant from the soil. And how we do that in 3 different steps. The first step is consists to heat up the soil. Why do we heat up the soil? It's just to vaporize the contaminants. And how do we heat up the soil? It's thanks to heating tubes. So we have a heating tubes going through the contaminated area. This heating tube is connected to a monitoring box, burner bodies, and the objective is just to have oxidative combustions and to generate hot air that will circulate along the heating tubes. The hot air will go to inside the inner tubes and then between the inner and the outer tubes, and like that we will have a homogeneous temperature profile on the heating tubes. The energy will go to the soil by conduction, and of course, it will increase the temperature of the soil. And thanks to the increase of temperature, we will vaporize the contaminants. So now we have the first separation. The first separation is done, so we have to recover the contaminants. And how we do that? It's thanks to the vapor tubes just near to the heating tubes. They are perforated and they are under negative pressure. Once the contaminant is vaporized, you just collect it. But once you collect it, the vapor, you still have to treat it, and the treatment can be in different ways. There are 3 different options to treat the contaminant. The first one is to use the Reburn. So that's quite something very specific of Amherst Technologies. We use the heating system as a vapor treatment unit at the same time. The second one is a vapor treatment unit. Sometimes it's not possible to use the heating system to treat the vapor. So we have to add a vapor treatment unit. And we have also a third option, which is a brand new innovation, which consists of neutralizing in situ the vapors. And that's a product is called Thermal. I'm not going to spend a lot of time on this topic because it will be the subject of other webinar. For this presentation, let's just focus on the first 2 ones. So the Reburn. Reburn, it's simple. You heat up the soil, like that you can vaporize the contaminant. Once it's in the vapor phase, you collect it through the vapor tubes, you can see here, and then you inject directly into the burner bodies. Basically, you can do that if it's hydrocarbons contamination. Even if you call it as a contaminant, basically hydrocarbons can be fueled, the diesel engine, from diesel engine, diesel oil, and you can just reuse it as a fuel. The beauty of the Reburn, it's, of course, you have 0 waste, and you can also reduce the fuel consumption. And that's the heating tubes that will heat the soil, collect the vapor, and also put the soil under negative pressure. Here, it just what it looks like in the real life, the Reburn mode. So to the left, you have in the in situ. So you drill and you put the heating tubes directly where the pollution stands for. And you have near to the heating tubes, the vapor tubes. And the emissions will be directly reinjected to the burner bodies, and we will use the combustions of the fuel, of the pollutant as a fuel in the energy. To the right, that's exactly the same principle, but instead of putting directly where the pollution stands for, we just firstly gather the different hotspots of contamination, and we build the pile. And through the pile, we will put the heating tubes. And that's the same. You have the vapor tubes near to the heating tubes, and you will reject the vapor directly to the burner bodies. So now the second option, the vapor treatment units. There are many ways to treat the vapors with a specific vapor treatment units, but the main one is to cool it down, the vapors, like that you can condensate as much as possible. And the non-condensable phases will go either toward activated carbon filter or a thermal oxidizer. I will just show you some pictures of this one. It was the first project near to Brussels. It was in France. The client was Exxon, and the contamination was hydrocarbons with residual concentration of mercury, quite typical. And so we needed to manage both contaminants. Other project in Sicilia, quite the same, hydrocarbons contamination, AV contaminated, and mercury. And the last one, it's about mercury. So it was in France, and we did a project with Englobe, and we need to treat below a building. We vaporize all the mercury into the soil. We collect the mercury vapors. We send it towards the vapor treatment unit, which was condensation and then activated carbon. But just to conclude, to make sure we have all the basic knowledge to understand the topic of this presentation, I would like just to jump on the most representative graph of thermal desorption. Here's the graph, and you can see on the y-axis the soil temperature and the soil temperature over time. If you take one spot of the contaminated soil and just follow the temperature, the progress of the temperature, you will see different stages. The first one is about increasing the temperature from the initial temperature to 100 degrees, which corresponds to the boiling point of water. Then once we reach the plateau of 100 degrees, you start evaporating water. You evaporate all the waters there. And as long as you have water inside it, as long it will take to evaporate it. So if I take an example here, I would say, as an example, 5% of relative humidity into the soil. If we have 10, it will be longer. If we have 15, it will be longer too. Then once we vaporize all the water which is present into the soil, then the temperature increase above 100 degrees and we'll reach the target temperature. Once we reach the target temperature, we take some samples. We know that the soil is clean and we start the fourth stage. That's basically the stage that no one talks because the contamination is done. It's already done. We get success. No, it's just to demobilize it. But for this presentation, let's just focus on the fourth stage. So the different methods to cool down the soil. Firstly, it's why we should cool down the soil. Just shut down all the electricity and fuel supply and just wait. There are many ways. The first one, we cannot do that for different reasons. The first one is the heat losses. If we just shut down all the installation, it means the decrease of the temperature will be only thanks to the heat losses. We can also have water, the rainwater that can go inside the soil, but basically it will be the heat losses at the surface and the edges of the contaminated area. And to give you a rough idea, because we did it one time, but to jump from 250 degrees to 50 degrees, it will take approximately 6 months. So quite a long time. The second point is a health safety measure, because basically I want to reuse my heating tubes. I want to remove them. I want to get back to the heating tubes. And basically, when the soil is at 250 degrees in average, it's really complicated to remove the out tube. So there is a safety point to address. And of course, that's a consequence. We have a longer mobilization. So even if it's not the main cost driver of a thermal desorption, it will influence our cost and of course the pricing. So now we understand we cannot just shut down all the installation. We have to do something. So the idea is simple. The initial point is an hot area and the end is a cold one. So you have to extract the energy. So if you take, if I take back the idea is if I just let it losses at the surfaces, it will take 6 months, maybe more if the temperature is higher. So now I have to be smart, and I have to think, what can I use to accelerate this extraction of the energy? And basically, we have a lot of piping into the soil. We have 4 types of piping. The first one is thermocouple tubes. So thermocouple tubes are intended at following the temperature progress. But this one, I don't want to use it because basically I want to follow up the temperature decrease. So I cannot use my thermocouple tubes. I have to keep them as they are. We have also the pressure tube, really important, the pressure tube, because we want to make sure that we are all the time under negative pressure. So this one, I'm not going to use it too. So there are still 2 points. If you remember the beginning of my presentation, we still have the heating tubes and the vapor tubes. So that's basically to extract the energy. We will use either the heating tubes or the vapor tubes. And basically here you have already 2 big types of cooling methods. If you use the heating tubes, is what we call the indirect method, because basically you will remove the energy thanks to the conduction inside it. If you use the vapor tubes, it's what we call the direct methods, and it will be more about the convection. But still at this stage, okay, we have the piping, so we know the way to extract the energy, but we still have to think about a fluid that will be able to capture this energy. And here we have 2, I would say, cheap fluids, water and the air. Here, just to give you some already quantified number, ambient air is able to capture 1 kilojoule per cubic meter of air to increase of 1 degrees. Water is 4 times higher. And now we can already find 4 different methods to cool down the soil. So now the remaining part of the presentation will be about illustrating the different methods to cool it down. Okay. So the first methods. So the first one, I will just take an example. It was in Belgium. It was an old Indian factory, but we are not gonna go too much into details about the project. Just know it. The contamination was TCPC. So the target concentration to make sure we can remove it, remove and reach the target concentration of 1 ppm was 95 degrees. So now we take out samples. We know that the soil is clean, so we just shut down the burners, and we will use the heating tubes as a heat exchanger. At the same time, we will keep the suction through the vapor tubes just to make sure, because in these specific cases, it was a groundwater near to the area, so the water can come vertically upwards or horizontally inwards to the soil. And so basically you have to be able to manage all the vapors, the fugitive emissions. And here is just the graph. So it was just only air circulating inside the heating tubes. It takes approximately 20 days to reach the target, the contractual target temperature that was 40 degrees. Other example, it's with an STD. So for this case, definitely, if you look the tree, it's not in Belgium, but it was a small pile, and a small pile in a former chloralkali process plant, and the soil was heavily contaminated with mercury. So target temperature to reach was 350 degrees. In this case, we take out samples, and once we say, okay, the soil is clean, now we have to cool it down. And here you can directly see the graph. It took approximately 25 days to reach 100 degrees. And there contractually, it was expected to reach 80 degrees, so we just stop it there. But if the contractual target temperature was 40 degrees, we can expect, as with my first example, 20 more days. Why is it faster? It's just because the density of the heating tubes. In my first example, it was 1.5 meters, the distance between the heating tubes. In our case here, it's 1 meter, so definitely the cooling also is faster. So at this stage, we can already jump to a quick conclusion about the first method. Firstly, there is no investment to do because basically you just shut down the burners. And that's all, just that cold air circulating within the heating tubes, and you are extracting by conduction the energy from the soil. Then that's really fast. There is no installation. You just shut it down, and that's all. You can start the cooling phase. Of course, it will take between 15 and 45 days to cool it down, depending on the target temperature and density. But it requires low consumables because you just need electricity just to keep running the fan and the blowers. And you can also use the same monitoring as a treatment. Basically, you're following the temperature, the pressure. You use exactly the same monitoring to follow up the cooling phase. The cons of this one, it's because you are working with a VTU, with a blower and a fan, even if you don't need 24/7 an engineer on site, still you need someone on site just to follow up and to make sure if there is any small issues to handle it quickly. So that's a cons because basically it costs money to put an engineer for 20, 15, 45 days. Sorry. And the last point also, it's you saw it in the graph, it's quite fast between when the temperature, the initial temperature in the tile is above 100 degrees, but when it's below, it makes sense. It takes longer and longer. So if contractually you are expecting a target temperature of 10 degrees, it could take a while. That's also something to take into account. The second method, so remember it, we are still using the heating tubes, but we are not using the air inside the heating tubes, but now we are using a liquid, water. So here just a draw to explain you the principle. You just, at the end of the process, you just shut down the burners, you remove the burner bodies that was just above the heating tubes, and you connect. You put a connection with a water network. Basically, I'm not going to spend a lot of time about this one because we can jump directly to the conclusion because it requires a lot of investment because basically you have to make sure that the water circulates properly within the heating tubes. You have to collect the hot water, you have to cool it down, you have to inject it, so you need pumps, you need a lot of new monitoring inside it. Of course, it's not so fast, so you will spend a lot of money on something that's not so fast. Definitely faster than the first method, but still, compared to investments, it doesn't make any sense. So let's jump directly to the third method. So the third one is we are not using anymore the heating tubes. We will use now the VAPOUR tube. To illustrate an example, so it's a project we did in the center of Paris, still within globe. And it was a contamination. It was soil contaminated with mercury. Maximal concentration was around 10,000 ppm, and the target was 50,000. So at the end of the project, quite the same. We reach the target temperature, we collect samples, okay, we reach the target concentration, we can start cooling it down. Quite easy. So here we have an illustration. We have a VAPOUR tubes, and the VAPOUR tubes, of course, is connected to a vapor network that will be up here, that's a pipe that was heated, that will be connected to the vapor tubes. You just disconnect this point. And you will disconnect 50% of the vapor tubes. And on 50% of vapor tubes, you will inject water. And the remaining part of the vapor tubes, you will keep sucking the generated vapor inside it, and you send it towards the vapor treatment unit. Because as you can imagine, it was the center of Paris, so if you inject water inside a hot pile of 350 degrees, it will generate a kind of big cloud. In center of Paris, it could be quickly a big mess. So I will just give you some numbers, some quantification when we are talking about injecting water to the vapor tubes. The first one is when the water is going from 11 degrees to 100 degrees. So you inject the water inside the pipe. The initial temperature is 11 degrees, and then the temperature will increase until reaching the boiling point of 100 degrees. And then for each degrees, for 1 kilogram of water, for each degrees increasing, it will capture 4 kilojoules. And once you reach the boiling point, basically it will capture for 1 kilograms, you will need 2000 kilojoules. It's not kilograms, it's kilojoules just there. So the pipe, initial temperature 350 degrees. You inject the water, okay, temperature will increase until reaching 100 degrees, and then boiling, evaporating. We collect the vapors. Then the pipe, the average temperature within the pipe will be below 100 degrees. And at this stage, theoretically, we don't use anymore the evaporation enthalpy of the water. We will just use the calorific capacity between 15 and 99 degrees. And this assumption we use, we got theoretically to bring the pipe from 350 to 100, we will need around 50 cubic meter. And then to bring the pipe from 100 degrees to 40 degrees, it was theoretically approximately 30 cubic meter. In reality, to reach 100 degrees, it was, right, straightforward. We did it quite in a few hours, but it wasn't exactly the same below 100 degrees. So one of the big lessons learned we had during this project is when the pipe is dry, basically you have a really good permeability. So the vapor can just circulate quite freely within the pipe. But once you reach below 100 degrees, the water, we start to put in water inside the pipe. And so we start getting kind of heterogeneous environment. And so there are no professional paths inside it. And so the water distribution will be irregular. So in this case, we stopped injection after 40 cubic meter. The average temperature was 80 degrees, and we decided for the end of the project to go back to the first method with, using the heating tubes and circulating air within the pipe. So, quick conclusion about the third method is a very low capex investment. To give you a number for these specific cases I exposed you in Paris, we are talking about 1,000 euro just to connect everything to the supply point. That's also a fast installation. It took us approximately 5 hours to connect everything. Low consumable required because we're just running the VTU, but just for a few days. These techniques we can reach to or in few hours, a few days to reach the target concentration. But still below 100 degrees, we still have an issue. It will take longer because of the operational path, and you still have to manage the water vapor. So you have to manage the water within the vapor treatment unit. But there, I only discussed about the vapor treatment unit. So you are using the heating tubes as one network, and we are using a vapor treatment unit as a second network. But what's happening when we are using the Reburn? Because basically that's the same. The heating system and the vapor treatment unit are the same heating tube and same burners. So it's already some deviation from the first method exposed you. Because basically, if we shut down the burners, we also shut down the vapor treatment unit and the water management. So there are two alternatives. So the first one, I'm not going to spend a lot of time on this one. It makes sense. It's you will add a kind of VTU, a small one, a small blower, just to make sure not to get fugitive emissions within the area, but to collect all the water vapor and to treat it, and to collect it. Here's just an example. It was a site in Brussels, and here's that's the simulation we did before cooling it down, and there that's the real temperature progress. And it was expected 30 days to cool it down, and at the end we cool it down in 30 days. Then we have also another one, but this one is really specific. It's essentially, if we are working with a large project, a large batch, you will reach the target concentration at some point at the beginning. Some will reach the target concentration, and some will require a few more days. So you can just use it at this point, and you can just shut down locally the burners. And that's why I exposed. That's why I exposed in these draws on the right. You can just shut down some lines, and like that, the water coming vertically, upward, or horizontally, inwards in the soil can be collected with the heating tubes. They are still running, and then you can shut down more area that already reached the target concentration, and so on until the end, or you can just stop everything. If I would like you remember 2 or 3 information about this presentation, the first one is when you stop the burners, there are water coming within the area, and this water coming inside it will definitely generate fugitive emissions. So you have to manage this water. It's not because you stop the burners that means you stop the suction of the installation. That's the first information. The second one is you can just let it go like that. You can let the heating tube inside it, but it will take 6 months, which is really pity. You will take 15 or 30 days to heat up the soil, and then you have to wait 6 months to cool it down. It doesn't make any sense. So you can use either the heating tubes or the vapor tubes to accelerate the cooling phase. If we use the heating tubes, basically we use only air because water doesn't make any sense in the investment, but it will take between 15 and 45 days. If you use the vapor tubes and you inject water inside it, it will take between few hours and a few days, depending on the capacity of the vapor treatment unit. With Reburn, you have to take into account it. You have to add a small installation that will capture, that will suck it out all the water vapor. And at the end, you don't have to add any monitoring to follow it up. You just use the existing monitoring that you used for the treatment. So thank you all for listening to me, this presentation. I hope it was really clear.
Well, thank you very much, Aurélien. I think thank you also for staying in the time. So I invite you, if you have, as I said earlier, questions to put them on the chat box. And I'd like to start with one topic you alluded to in the beginning, the reason why we do that, right? And there was one thing that I think you didn't really address is remoisturizing the soil and the relation with stability. Can you expand a little bit on why is this a condition in particular, especially for ex situ, because the soil, when it's heated above 100 degrees, it's just one big dust cloud, isn't it? So so could you relate on that, on also the use of the reasoning, or why we clean, we bring water in there?
Yeah. I will just start with the ex situ, and then I will expose you an example with in situ. Ex situ is very important. I will just jump back to the example I showed you. It was the small pile with mercury. So we heated up the soil up to 350 degrees. And so basically, once we reach this one, the soil is really dusty. And so when you cool it down, the soil, and then you just remove the concrete on the top of the pile, and you start handling the soil and to put it back in the initial state, you will get a lot of dust inside it. So it will bring a lot of new safety measures, or a lot of points inside it. So I would say from an operational point of view, it's way easier to put back the moisture. Other example, it's in situ. I will take just an example under a building. Basically, we are not working with drastic incineration techniques. That's something quite low. So we do not affect the structure of the soil, but still, if you are working in a clay, soil which is clay, that can contain up to 40% of moisture. What you can see working in situ, you can get in a small location kind of subsidence, so the soil can just decrease a little bit. And that's also something that it depends on the different situation when you are working specifically under a building, but basically put it back soil, water inside the soil allows to get back the initial structure of the soil. So that's two different ways to do moisture, and also that's in the conclusion. But if you are using air, it will take between 15 and 45 days. If you also using the water, you can decrease this time to 2 or 3 days. The fastest one I did was in 6 hours. So when I started, 6 hours after, it was 70 degrees.
Yeah, the point was also that no matter what technique you use, at the end you will have to put water inside, because if not, you will not bring the soil back to its initial structure or texture, which is what you need to do.
Yeah, totally.
And I understand also for our audience that it's the critical part in injecting water in soil that is above 100 degrees. Because soil is hydrophobic. I remember that from all our old days in the rotary kiln business, where the big issue was to cool down the soil. And it was very difficult to cool down the soil. Mm-hmm. And in the soil cooler, in the pug mill, if anything went wrong, we had huge dust clouds, because if there is no water in there, that soil is just it doesn't have any cohesion. Yeah. It's the same here, other than you can take more time to remoisturize it and not have these explosions which you have in hot soil.
Okay.
I have another question. You showed an example where you cooled down. I think it was in the first example you showed. You cooled it down in 20 days.
Yes.
And if I'm not mistaken, in that example, the reason why it was so quick was that. Is that a matter of the fact that it's outside, it did rain? Because it's you didn't inject water in this case. So it's just by using the heating tubes as heat exchanger, which is which is conductive. Essentially, it's a reverse of conductive heating. It's conductive cooling, but it's not very effective because it's just air, as you showed. It's like 4,000 times less energy in 1 cubic meter of air and 1 cubic meter of soil. But you still managed to do it in 20 years, in 20 days, sorry. But if I see it right, it was not very clear. You started from a much lower temperature than the next example, where you started from a much higher temperature.
Yeah, totally.
So does that play a role, the fact that there wasn't a lot of water to begin with? I mean, or that the temperature was low enough, or there's maybe residual moisture?
In this specific case, we were the heating tube. The bottom of the heating tubes were almost it was near to the groundwater table. So if you don't have any energy sink, so the water inlet coming vertically.
What you call an energy sink is water coming into into the area.
The best way to remove energy is definitely water. If I compare it to the air, but in specific cases we use the heating tubes by conduction with the air, but at the same time, I didn't expose it to you, but at the same time we were water coming from above the side. So here it was 20 days to cool it down, but it was more expected for 40 degrees. If we don't have this energy sink coming from the bottom, it was expected something like 40 days, 40, 50 days. And also, I think that's also right, really important. You can see here decrease is quite linear, I would say.
So there, degree,
and there it's coming like a asymptote. It's really complicated to reach 40, 30, 20, 10 degrees.
Yeah, the last one,
much more. Which is totally different from this one there, because the temperature difference between the pipe and the environment, it's, at this point it's almost 350 degrees. So there are a lot of energy extracted, and then here you can expect asymptote there. Okay. Or you can inject water, you can accelerate the point totally.
And that's why I was just emphasizing the difference also, because of course you don't start from the same point.
Yeah. Totally.
And that brings me to the next one, where you have when you use that first that not the first but the other method, where you continue to extract vapors from your vapor tubes, no matter how you do it, whether by injecting water in other vapor tubes, which is third method, or by continuing to use your heating element now as cooling element, conductive. Would it be advisable to now increase the negative pressure? Because as you explained in the previous webinar, while we heat, we try to keep the whole pressure negative. You explained about your pressure pipes, pressure tubes, which are there to make sure that there is always a negative pressure, but very negative, very low, like typically, I think you said about 0.5 millibar or something like that. And the reason why that is you don't want to attract cold air in the system. Yeah. Because that would cool the system. It's like heating a room. We put sweaters on because we don't want to open the window. I guess it's another discussion, and that's why you alluded to maybe put another blower, because now you can go to much higher negative pressures, because that would attract cold air, which is what you try to do. Have you done that in one of these projects?
Firstly, what you are exposing, it's the fourth method. I didn't spend any time on this presentation on this point, so that's really good question. I mean, firstly, yes, we could do that definitely. We can just increase negative pressure inside it, and so you will increase as a consequence, you will increase the cold air going inside it. So you could also extract by convection. By direct contact, you can extract the energy. Basically, that's something that happens, I would say, all the time, because when you are cooling it down, basically you are not injecting any more energy inside the soil. So basically, you are not generating vapors. So if you are not generating vapors, basically the pressure, the negative pressure will increase.
But the porous media, as you said earlier, the soil has a huge permeability to air because it has no water. So you can easily get a lot of flow through it by applying negative pressure.
Exactly. But basically, just to conclude about the first method, basically, you are using the first one, second one, third one. You will all the time use the fourth method, but you could accelerate it. At this point, we have already done that, but we haven't increased drastically the pressure into it. So we should do that. I'm just thinking in terms of investment, the blower has to be slightly different. So it means also you have to adjust a little bit this point. So my spirit is I should use the first stage is basically the stage that no one cares. So my spirit is I'm not going to spend a lot of money inside. I will try to find something that's fast, but that will use the existing equipment.
All right. I just see another, I was just going to close it, but I see one on LinkedIn a few days ago. There was a post about a new HEMIS patent. Can you briefly explain on what this improvement is about? Which patent was that? I have to.
The VX.
I will have to come back to you on it. I just know that we had patents. We had a few, but there is definitely one on the new burner, which is it has nothing to do with cooling, but it's the fact that we have launched a burner that is no longer the same design as this one, but is a completely different design, and that one will have a 30 to 40% fuel consumption reduction based on the current one for the same energy injected in the soil. And then we had a recent one also on the thermal react, which Aurélien alluded to, and which was not the subject of this and will be subject of a specific webinar. There's already been one. But really my apology for not directly seeing exactly which one, which patent we've alluded to. But I'll get back to you on that. So it rests me to thank, first of all and foremost, Aurélien for this nice presentation. I think the topic was worth it. It's, as you say, mostly underrated and we don't pay attention to, but it's a very important one. Thank you all for participating. We really appreciate it. Should you have more questions or contacts, just questions, don't hesitate to come back to us. We'll get back to you very on every single question. Oh, just before I see this new patent autonomous. Okay, that was the new burner I was talking about, and it's the fact that the burner can now work on its own and essentially regulates the fuel consumption and the power injected. So it is related indeed to the new burner with a substantial reduction in the fuel consumption. I'll invite you on that. We'll probably have a webinar on that one as well in the coming weeks, or probably a month and a half about it. So let me then wrap it up. Thank you again. This is recorded, as I said earlier. It is recorded. You'll be able to get it. If you have any details of contacts or projects you want to discuss, of course we are open. You know who to contact, and rest me to wish you a very good day for those who are waking up, very good afternoon, or very good evening for those who are finishing their day, and see you for the next webinar in a couple of weeks. Thank you very much and have a good day.
Thank you all.